So let's talk now about the action nodes. There are two different kinds of action nodes. The first one simply called action node, and the second one which starts with the word differential. We'll see the difference in a second, but for now let me talk about the first one. So I'm going to add it to my tree, and then I'm going to inspect it. And the first thing you can see is that it defines an event. And this event will take a public void method that takes as arguments a string, which refers to this parameter, an action node, which refers to this action node, the one invoking the event, and the game object, which will be provided by the Koala brain when it ticks on this node. So when you implement it, when you implement the methods, you can take for granted that whatever you write here will go to this string. This action node will refer to the node invoking, and the game object will refer to the actual game object with the Koala brain that ticked on that node. I hope that makes sense. So I'm going to create a new event, and then the library contains two scriptable objects that hold methods that we can use. The first one is this Koala move action, and I'm going to put it here, and you can see that it just has two predefined methods: move to a vector and move to that vector differentially. So the second one is best suited to be used with the differential action node. So I'll select the one without the differential node on it. And this will need a vector 3, and also it will need the speed at which it will move. I can change the name of the action node here, so I'm going to call it move to origin, and you can see that it changed also in the inspector. And then I'm going to reset its status, and you can see that as soon as I click on it, a new button appears in the details of the node where I can tick just this node. Now the event right now is set to be invoked only during runtime, but I can change this to work in the editor too. And right now, if I change the position of my NPC to something like, let's say that, and then I tick on my tree, you can see that it performs the action that is defined by this method. Now, one thing important is that although it already finished and it took the game object to the target position, and that the coroutine, the underlying coroutine that drives this movement is already finished, my tree says that the action is still running. This is because I need to tick again on it to check its current status, so the next time it will return true. And if I tick again, it will be called again, but since it's finished, now it will return true. Let me show you how this method is implemented. So I will go into the scriptable object move actions, and again you can see that it uses the namespace Koala BT. Then it has this attribute, so I can create it with my context menu, and then it inherits from a standard scriptable object. Now this is the method that I'm using, and you can see that it first just parses this string s into different values, and then I take the speed to be the last of those values, and then I create a vector with the first three values of my parsing, and finally this is the important part. I am starting a coroutine, and this coroutine will take more than one tick to finish. So I need to be able to yield on it, and this coroutine is starting this IEnumerator method, which is called move to, and it takes a vector 3, a speed, an action node, and a game object. The node is provided by this method, and as I told you, it's the node that invoked the event. And the game object is provided by the brain, so you can simply pass them to the enumerator, and then the vector and the speed is what we parsed from the string. Now, the important part of this is that the result of the start coroutine, which is a coroutine, is assigned to the node dot my task. So now the node invoking the event has a running task, a coroutine attached to it, and it knows about its status. This is very important because if we want to later stop the coroutine that the node produced by invoking the event, we need to know which is the coroutine that the node is running. Now the coroutine itself is a standard moving coroutine, and it has this while loop that checks whether the game object is where it's targeted to be. Then it moves, it adds to the position using time.delta time, and finally it yields, so that each time it goes into, it will check the condition of the while loop, and if it's not there yet, it will keep on looping. But once it reached its destination, and this is the other important part, it calls a method within the node with the status it wants to set. So right now, when this happens, the node is aware that the action finished with a success. So this is what I have to call at the end of every coroutine to tell the node that it finished the action it invoked. And then the next tick, it will return us this status. So that's the basic idea of how to set up a coroutine. And you can see that the coroutine needs a game object to be running. So I'm using the game object Koala memory script to be the base of my coroutine. So this is the script that will be responsible of running this coroutine. And yeah, finally you have this node.action debug info, and this is a string, and this will give you the information that you can see next to the node in the editor. So for example, if I reset my status and move this one again and I tick on it, you can see that there's information about the position of the game object here. That is set up with the this line here, where the action debug info of the node is replaced by this new delta to string information. So that would be the way to implement actions that take more than one tick to be finished. Now, the other node with standard actions is this Koala wait actions, and you can see the methods it includes. You can set up to check if a key is held for enough time. You can wait until next key is down, and wait for any key down, for any button up or down, for keys, for mouse buttons, for seconds, or for ticks. And these things look like input conditions, but they're actually waiting for something to happen. So that it takes more than a tick to know whether this succeeded or not. So it's implemented as a standard action. Now these kinds of actions, the ones that call coroutines, actually sort of kidnap the working behavior tree. What do I mean by this? Let me go to the scene that's set up to work with play tag game, and if I look at the play tag example. Let me put this tree here. Okay, and now I'm gonna play it. And you can see that the white cube moves to a destination and it doesn't check anything else in the tree until that that action is completed. And when it's completed, then it runs the previous nodes again and checks whether it's it or not. So while the coroutine is running and the node is set as running, even if I tick on the tree, the event is not invoked. The event is only invoked when this node is not running. So they sort of kidnap the tree in the sense that they will be the only thing that the tree does until the coroutine is successfully ended. That means, for example, that if I want to change whether the game object is it, I have to stop all coroutines so that it doesn't keep on going uh, after I changed its status. And you can see this in the play tag memory script, and you can see that when it changes who is it, it stops all coroutines. So this is a specific behavior that works for specific things, but you may want another kind of action that is sticked every time the tree is sticked. So that kind of actions are called the differential actions. And I will show you examples of it and how they're implemented in the next part of this video. So see you then. Bye.